So our next speaker is joining us virtually. I can already see Bettina, that she's there, so that worked out. Bettina, I'm going to introduce you while you're there. You are. Okay, so Dr. Bettina Sorger is a psychologist and an associate professor at the Cognitive Neuroscience Department at the Faculty of Psychology and Neuroscience at Maastricht University, that's in the Netherlands. And Bettina Sorger has worked in several fields of fundamental and clinical neuroscience with a focus on developing methods for brain-based interaction and neurofeedback learning, exploiting hemodynamic signals. So currently her particular research objective is the transfer of fMRI methodology and results to mobile fNIRS to increase usability of hemodynamic BCIs to provide patients instantly and permanently with useful BCI systems that are applicable in daily life. So this is pretty much in line with the theme of our conference. So Bettina, we see you. I don't know, I hope you see us. And I'm assuming you'll have to screen share for us to see your presentation.
Good afternoon, Boston. Many greetings from the Netherlands. So maybe this gives me already the possibility to thank the organizers and sponsors of this event that I can attend virtually and that I can attend at all here. I'm very excited to be here. I really hope that the Zoom effect or Zoom face effect mentioned earlier today will be only marginal in my case. So in order to counteract, I actually have also prepared a mini live BCI demo at the end of my presentation. If time allows, I hope that this will work out. Okay, so brain-computer interface, and what does it mean? It's a methodology that enables a direct connection between the brain and an external device, which can be a computer, for example, and the meaning and purpose is to allow a user to motor independently act in or interact with the outside world. And the hallmark of this is that we immediately lose brain activation, that it's just measured. That means we really need online data analysis software for that. To give you an overview about the general setup and operation of any given BCI, so we have a functional brain imaging method that measures the brain activity of an animal or a human, and the signal is digitized and enters the signal processing unit. And during this process, a meaningful feature from the fNIRS or whatever signal is extracted, and this feature is also related to a specific command in a translation algorithm. And then you can control devices, for example, a letter speller, a wheelchair, a robotic hand, or also a neurofeedback display. Here we are then already at the main application possibilities of BCIs, which is neurofeedback learning and therapy on one hand, and interaction BCIs. And the reasoning for neurofeedback learning and therapy is that everything what we do, everything what we perceive and so on is represented in the brain, and also disease is somehow represented in brain activation, in abnormal brain activation. And this means that theoretically it's possible to influence human functioning and also diseases by changing brain activation. So there's only one problem, that neural activation is on a normal conditions not accessible to our consciousness. So therefore we need neurofeedback to bring this to our consciousness so that we can monitor and modulate brain activation in a desired direction, and thereby also resulting in desired behavioral changes. So this is the reasoning for neurofeedback. For interaction BCI, the motivation is also very clear. Human interaction with the world requires the functional integrity of the neuromuscular systems, and in some severe diseases, motor diseases, people are not able anymore to naturally interact with the environment, and they can be still conscious and awake. And this is a terrible situation, and we need to provide these patients with alternatives, motor independent alternatives, and these are the BCIs. They replace the lost motor functions by using voluntarily evoked brain activation. So this slide should just make clear that the huge majority of BCI research has done in the EEG domain, so using neuroelectric signals. Another modality is MEG, ECOG, intracortical recordings, and also more recently stereo EEG. This is one side. The other side are the hemodynamic BCIs using functional magnetic resonance imaging and fNIRS. And this is what I have been working with for most of my time as a researcher and also as a PhD student already. And this I will focus on. Before I start and introduce you to some developments, I would like to familiarize with the BCI relevant characteristics of hemodynamic signals, because it's very important to know them and to work with them. So first of all, the delay. In contrast to neuroelectric responses, which are immediately after a stimulus, like here a short visual stimulus, the hemodynamic response is very delayed and extended. So the signal only arrives 3 seconds after in this case, the stimulus is already gone, and it takes up to 10 seconds until the signal is back to baseline. This is, of course, not so advantageous for BCIs. What is good is that we have in hemodynamic functional neuroimaging a high single trial reliability. So that's what we see here, 20 trials of a motor task. You see almost in every trial an increase in the task periods, which is the red periods here. And when you average, you really see the prototypical hemodynamic response. What is also quite good is the spatial resolution is, of course, not as high as intracortical recordings, but it's better than EEG. And we see, for example, here, for the performance of 3 different mental tasks that we have, of course, overlapping areas, but we also have quite distinct areas, which is good for differentiating these mental tasks, because we use them for encoding information. Yeah, why do we use these mental imagery tasks? Why don't we use just thinking? I mean, it's just, I would say, not yet possible. I mean, recently we have seen in a study from Tong et al. That it's possible to decode semantics with fMRI, but if you look at the methods, you know that 16 hours of training data has to be acquired. This is nothing what we can use already for BCI at the moment. So, but people need, of course, help now. And for now, we go on with this indirect encoding, which means we let subjects perform a motor imagery task, for example, and a mental speech task. And so we have 2 information that we can differentiate, because both tasks are very nicely differentiable in the brain. And what are then the hemodynamic signal features that we can exploit? First of all, spatial, as just demonstrated, for example, for the 3 different tasks that I show here. Or we use temporal features. As we have a high signal trial reliability, we can reliably detect start and stop of a signal. This we can exploit, and also theoretically magnitudinal signal features. I have tried that in my PhD, was not that successful, so therefore we concentrate on using spatial and temporal features. So when I started with this research, there was this study from Owen et al. In 2006. We're just coming out, and I was really kind of intrigued by this study, showing that if you ask a patient, it was a patient thought to be a vegetative state, to perform mental imagery tasks, they saw prototypical activation patterns that you find in healthy subjects. And the only logical interpretation was that they are aware of the situation. Then later, these researchers have developed also a communication paradigm, so that they were even able to communicate with such a patient. And my supervisor, Rainer Goebel, and I, at the time, we were really thinking, let's push fMRI to the limits. How far can we come with fMRI? And first, we developed a 4-choice communication paradigm for fMRI, and later then fMRI-based letter speller. And the idea is quite simple. You combine the signal features that I was talking about, the spatial features, the temporal features, and you end up in 27 distinct dynamic brain activity patterns or brain activities. And so, for example, for the letter D, you have to use motor imagery, and you do that after 10 seconds after the general trial onset, and you do it for 20 seconds, and then you end up in a unique brain response. And they do not have to keep that in mind. They are guided by a letter encoding display, and so it's facilitated by that. So that was quite promising. We had letter decoding accuracy across subject of 82% with a chance level of 3.7. But of course, when we looked at our goal, which was helping locked-in patients, for example, that was not so meaningful. So it was not that we could really provide participants or patients with what they really need, namely convenient, straightforward BCIs that work in everyday life. So I was thinking, oh, let's put this together here. What are requirements for clinical BCIs? And next to the high functionality, it should be 100% safe, no risks, etc. It should be durable. It should allow for individualization. Should be comfortable, user and also operator friendly. Should be affordable, because it should be something that you can use in everyday life and for the rest of your life. Actually, you need the system at home. But most importantly, it should be usable in daily life. And that means independent of place and time. It should work. It should be compatible with other equipment. It should be mobile, compact, and robust. And yeah, hopefully low sensitive to motion, and should be little prone to failure. And at the same time, I mean, if you think like this, we were developing things for the everyday life. BCIs are, yeah, kind of the application for real life applications. We need also a naturalistic patient-centered approach with this focus on the usability in the everyday world. So I was also thinking, what are all benefits of using functional imaging in the everyday world, next to those that were already mentioned today, namely that we have more behavioral that we can study. There's a lot on the side of the participants, and actually it was quite striking when we went for the first time out of the lab. Because of Corona, actually, because of the pandemic, we could not scan in the lab. So we said, okay, let's go out. We go in the cafeteria because this was a lot of space and you could have distance and so on. What we realized quite immediately was that people are much more alert, pay more attention, were higher motivated, and they are also less physical and social isolated. And this is an advantage for later application, namely the presence of family and caregivers is possible all the time then. Yeah, for the study, we have less confounding factors through the lab situation. It means higher external and ecological validity of the results. And also we can combine neuroscience methods easier because it's not in the lab, it's outside. And what I also like to mention is that also the participant-experimenter interaction is much more given, because I remember when I was an fMRI subject lying in the scanner and thinking, oh, I have to tell that to the experimenter later. I totally forgot when I went out because I was just happy to be outside again. And finally, some last advantages are for the experimenter, for example, cost saving. So I don't need to pay lab fees at the moment. That's very nice. And I have to say also the logistics of planning experiments is much easier. This is not complete, probably you have much more ideas here. So then let's look at fNIRS as an BCI input modality. What are the advantages? First of all, we have two dependent variables. We have oxygenated and deoxygenated hemoglobin changes. And this comes along with more robustness for the analysis, but also more certainty of the decision, for example, of a decoder. It is non-invasive, safe, is it nearly noiseless, as is compact equipment. We can apply it in any body posture position. It's relatively cheap, and the maintenance costs are really low. It's not vulnerable to electromagnetic environment, compatible with paramagnetic equipment, is relatively easy to apply, and low sensitive to head motion artifacts. But the best thing, of course, it's portable, mobile. It means we have full environmental flexibility. Of course, also some challenges and limitations. How I see it here in the BCI context is fNIR is only an indirect measure of brain activation, and this is especially for the neurofeedback applications maybe point of attention. The same is also applies to the spatial variability of brain anatomy and function, and the lack of individual anatomical information with fNIRS. What also is very obvious is the high variability of fNIRS signal quality across individuals, which also is demonstrated then in the results. I will show this later. And then the artifacts that were mentioned already this morning. discussed a lot. And then we have many limitations, like the temporal resolution is limited, the spatial resolution, the coverage and depth pervasion is limited. So far also the fNIRS equipment is not as flexible as I would like to have that, but I think there will be changes in the future. I've heard about it. And there's something I would also like to put attention to. These are the blind spots, as I call them. It's namely that there are brain regions that are, from my point of view, suboptimally covered by the fNIRS montage. For example, here, when you measure between a source, here in red, and a green detector, then you have a nice, you have nice sensitivity, but between two sources and between two detectors, you are less sensitive. So this is a problem, and we cannot address it so far. Now I would like to present some example fNIRS BCI studies from Maastricht University in which we have addressed a couple of these challenges that I mentioned. The first study that I would like to present is an fNIRS-based decoding of mental state. The key objectives here were we wanted to investigate the neurocorrelates of 8 different mental imagery tasks, and we wanted to see how we can classify these brain activation patterns on a single trial level for BCI use. Then we also explored at the same time the usability of individual mental imagery strategies. So this is the montage and experimental design. I would say 60% of the cortex we could cover with 16 sources and 24 detectors, a huge setup, cost a lot of time to set up. We used the old NIR Scout at that time. And you see what the design was 4 runs with 12 trials per paradigm, among others, mental talking, spatial navigation, and so on, but also the own paradigm. So we used an own paradigm to ask subjects, what kind of a strategy can you imagine, can you perform best? Because we think there's a correlation of the subjectively experienced task performance and the brain activation strengths, let's say. And here you see, this I would like to show to, for one subject, individual activation maps. Here, one of the best subjects, that we have a striking consistency of HPO and HBR for the different mental tasks, but also to fMRI data of this particular subject. So if you look, for example, here, this spatial navigation, you really see almost, very similar. The spatial resolution is a little bit lower, but very, very promising, I would say. And here are the results after using SBM classification. All subjects, for all subjects, we achieved significant results for oxy, deoxy, and for the combination of both. So actually, a combination of oxy and deoxy resulted in the best results. The group mean for deoxy-oxy use was almost 46%, with a chance level of 12.5%. But you see the individual accuracy varied from 30 to 60%. And when you look at the 2-task classification accuracy, you also see that generally the 2-class classification is quite high for all mental task combinations. The theoretical chance level is here, of course, much higher, as 50%. But the group mean was about 77%, and also here we had a huge variation across subjects. So what is nice is that if you have so many task combination and the subjects differed also according to the different task combination, there's always room for individualization. So you might figure out for a particular patient also which task pair is the best. And also for maybe you can go with what they like to perform. So in general, it were highly promising results. However, we used a large fNIRS montage, and this is not practical. So therefore, our lab is following another approach for quite some time already, namely not to say we obtain as much as possible data. In that sense, I'm a little bit different than most people at this event. I try to say I want to acquire as minimal as possible and still get good results. And this is what we call the single channel approach. I will come to that in a second. So here I would like to introduce you to a very recent study from Anna Vorreuter. And the key objectives here were further develop the single fNIRS channel approach. That means just using one single channel, because it is for something what you will use in daily life is much advantages to that it's small, that it's not heavy, and that it's not visible even. Of course, it can be also 2 or 3 channels, but just to make it clear, we focus for now on a single channel, because we also saw that 2 or 3 channel doesn't matter. Then we wanted to increase the BCI efficiency and convenience by decreasing the information encoding time. So mostly study used 10 seconds. We also already used 6, and now we went to 2 seconds. So really only a very short cognitive event. And we also tried to increase the naturalness of answer encoding by linking the content of the encoding strategy to the meaning of the to be encoded information. That was yes and no. And we also used complementary fNIRS montages to increase fNIRS sensitivity. I explain in a second. So the information encoding worked like this. We used a combined motor speech imagery paradigm. And for encoding yes, we asked the subject to imagine, to draw a check mark, and at the same time saying, yes, that's true. So this is what I mean, is this semantically linked to the to be encoded information. And for no, they should do cross something out in their mind, and to say no, that's not true. And this ended up in 2 seconds periods. Here are the 2 complementary Optut setups with 9 sources and 8 detectors. There was also a single channel, a short distance channel included. And here you see the experimental design. So one single trial consisted of a yes and a no period, and the subject was supposed to do the yes or no strategy during the period that was assigned to yes or to no. So we used the temporal encoding. We had in total 100 trials per participant in 10 runs. And we had the subject had a question and should first part answer correctly, and in the second part should encode the opposite in order to have the same number of yes and no answers available. There's no bias. Data analysis was quite straightforward. My credits here go to fNIRS, who has programmed Tokusatори software. It's a great software that can be analyzed the data online in real time. Data analysis was standard pre-processing, including short channel regression, and we analyzed the localizers in that sense that we looked for the most promising channel by chromophore combination. And then we used this channel by chromophore combination for the encoding runs to decode the answers. And this was just simple extract time course and do a GLM with the 2 predictors accordingly to the 2 different encoding periods. And here are the results. You see, these are the subjects. This is the whole run accuracy, so 10 trials analyzed in common, and here the single trial accuracy. And you see that on average, we reached 68% across subject single trial and 86 whole run accuracy. You also see here a huge variation in the subjects and performance, in the BCI performance, but the huge majority could really use this technique very well. Now I would like to go one step further and to introduce to you the 4-choice fNIRS-based communication, BCI, by Bettina Sorger, a former PhD student of me. And here we really wanted to increase the flexibility of fNIRS BCIs by using different sensory encoding modalities, so visual, auditory, or tactile. We also wanted to demonstrate stability of fNIRS performance across time, and finally also the feasibility of using an fNIRS BCI in the everyday world. Here again, it's an extension of the yes-no temporal encoding period designed. So we have a trial, and we have 4 different periods, and depending on which answer you want to go for, you encode in this particular time period. And we had this by using auditory cues or visual letters that were presented to instruct subjects, or tactile. We just used the fingers as help. So the A was, for example, associated to the index finger. We had 5 trials per run, and we used the strategy, the mental drawing task. The optimal montage was 8 sources and 8 detectors, and experimental design you see here. We had the 3 sensory modalities. All was balanced across the 3 days that were tested, and also across localizer runs and so on. We had 6 answer encoding runs per session, per task. And the data analysis was similar to the analysis I've shown for the yes/no paradigm already. So we checked, we had the GLM with the 4 predictors accordingly to the 4 different encoding periods here. And the results were as follows. We had a mean accuracy run on a run level of 85%, which is very nice, and by chance level of 25%, and accuracy on a single trial level of 62.5%. And also here you see some variation. But what was really nice is that the 2 subjects tested in the cafeteria, so in real world, were one of the best subjects, but also BCI novices achieved quite nice results. And here you see the effect of sensory input modality. For all modalities tested, it worked out. And actually what I was very happy of is that the tactile domain works so well, because the tactile domain is also something which you can nicely integrate in everyday world environments. It's also not visible for other people. It's unobtrusive in that sense. And here the effect of time, you see here there was no huge decrease of performance across time, but also not a huge increase, meaning there is also not too much of a training effect. So to conclude, I hope I can convince you that fNIRS constitutes a promising functional neuroimaging method for BCI and neurofeedback applications to treat neurologic and psychiatric disorders in the everyday world. I think it's also potentially suited for long-term repeated BCI training and use, even in difficult populations such as children and patients. Of course, more research is necessary, but I'm sure they will come so that NIRS can develop its full potential. So I would like to thank the organizers again, and sponsors, and the audience in Boston all over the world. And my acknowledgements go also to all my collaborators at Maastricht University and at different other research institutes, and to the sponsors, to the fundraiser. And I would like to finish with a 5 minutes mini live demo in which I would like to demonstrate you the functionality of the fNIRS for choice paradigm. I think it's nice that it's available also to really analyze some data real life. So I hope you can see it. So by that you see that it's quite easy to set up a system yourself, which is also nice for later when patients maybe do neurofeedback at home. Maybe they can be supported then by their relatives. I do it myself now. Few things, steps.
The overcap.
It's very important because I have light from the top. Okay, so I now switch to Aurora to do the calibration, of course. I know that normally I should not talk, but it also works when I talk. So I have to say that my physical features, let's say, are very promising in that sense, that I have only little hair, very thin hair, that helps, of course, for the signal quality. So what I do is I have done the experiment already before, and this is what you see. It's a motor imagery experiment, and you see especially here in the primary motor cortex for the hand region a nice channel. You see in my case, Oxy HB works best, and therefore I'm using this now. I would like to introduce you to the display. Maybe a little bit complex, but what you see here is are 4 different trials. So this is the first choice, second choice, third choice, fourth choice. We have these 4 times here because I thought I would do 4 trials. In the test, I encoded A, B, C, D, or 1, 2, 3, 4. Maybe David can choose whether I should encode the same again or maybe the reverse order. It's nice that you really see that's nothing prepared. So what kind of order should I encode? A, B, C, D or C, D, B, A? What do you want?
B, C, A, D.
Oh, that's extra difficult. Can we do it because the thing is that I have made the pauses quite small in order to have more trials. So I would like to ask you to ABCD or the other way around.
DCBA then.
Yeah, okay, so then I do the reverse order then here. Okay, so everything is prepared. Yeah, the signal quality was also good. And now I go on. So you see here is the window, the output. Here, this is what you should see in here also in a second, but it should then start with 4, 3, 2, 1. Let's see how well it works. Again, I use the deoxygenated hemoglobin. So at the moment when I do the task, the signal should drop. Okay, so that you will see it's online data. I will remove the cap. You see the artifacts. So I think it went really nice. Thanks for your attention. And yeah, it was fun also to do this mini demo. That's actually the end of my talk. Thank you for your attention.
Thank you, Bettina, this was very suspenseful. And I'm assuming there will be quite some questions. So then now we have a bit of time. How much time do we have? 5 minutes? Okay.
Bettina, that was phenomenal. Could you explain to us what we all saw in each of the 2 panels at the top and the bottom?
Did you hear that?
No, sorry. Can you repeat?
Okay, so Swati was asking whether, so this was great, but could you explain a bit more what we saw in the top and in the bottom, basically in your, on your screen? It was a lot of information. I think everybody.
Okay, that's true. I'm still quite a data moment. I stop it. So then let me explain a little bit more what you see. Basically, here are the 4 different trials. One trial consists, or this is one trial, it consists of 4 different answer periods.
Sorry, we just currently don't see your screen.
Oh,
but
yeah. Yeah, you're right. Okay, so what you see here is a single trial, let's say, to encode either the answer A, B, C, or D, or the first, second, third option. The encoding works like this, that you perform the task in the particular time period. It costs, of course, time, but the shorter you can make these periods, the more effective is the BCI, actually. And here, this is the time across time. Here you see 4 of these trials. Always the red is linked to the first answer option, and so on. And what you see here is from one channel, from the channel 2.5, which we had identified before as a channel of interest because it showed really nice task-related brain activity for the deoxy. The oxy did not work so well. I mean, also okay, but the deoxy was much better, so I went for this. And therefore, I selected this channel. So we really look at only this one single channel. And then, that was said that I should go for the encoding of C, A, the order of it. And then you see here that my brain signal stays more or less stable. There's a little bit of variation, probably Meyer waves, until I come to this 4th option. And here I started to perform the motor imagery task, and the signal drops and goes back to baseline. And now you realize why I wanted to encode not immediately A after that, because the period is too short. But still, I mean, this was just nothing to do with the functionality. This was just to be more effective in this case. So here you see the signal drops already in the 3rd answer option because I encoded this option, and then it drops in the 2nd, and here finally it drops in the 1st option. And this was what the decoder is doing, basically different kinds of analysis, for example, multi-filter correlations or a GLM, and you see all different kinds of analysis all go in the same direction, saying, okay, answer option 1, which was the red phase, winner, and then it comes up with a kind of ensemble voting, what the decision should be. And this is what we see here, no? That for the 4 separate options, you see the decision of the decoder, and it was as I wanted to encode it like 4, 3, 2, 1. Is this clear a little bit more?
It was very helpful, yes. So maybe we have 1 or 2 questions left, if there's any. There's one, yeah.
Thank you so much. Very nice talk and very impressive live demo. So in the middle of your talk, I just have one quick comment. In the middle of your talk, there's a list of very beautiful, like, technical limitation of fNIRS technology. I've always been thinking about those technology, like something we can be more advanced in fNIRS when I was in David's lab doing my postdoc. And the last one, you use a little like figure to show, this one, to show that, okay, we can form a channel between a source and detector, but not between the sources or detectors. But actually in Alex's slides, he also showed that we can overcome this using a high density design of a montage, and then we will have a more homogeneous coverage of the brain. And then we will also have a higher sensitivity, spatial sensitivity to the brain. Just to mention that. Thank you.
Yeah, thank you for this this comment. Indeed, I mean, I don't know whether it became clear. This is what we really wanted to do with this montages here, to cover here, for example, this region, or let's say this region, much better with changing the position of the sources and the detectors. Actually, the best would be that we can have, I don't know whether it's technically possible, maybe a question to Alexander, whether it's possible to have a source and a detector at one location. That would solve the problem. Maybe this is a question that I have to him. What do you think about it?
Okay, well, I think with DOT we don't need that to get basically spatial sensitivity that is mostly uniform. I'm really happy to talk about this offline. I think actually what it shows is that there's probably a lot more possible to even further boost this already quite impressive example that you gave. So this was very inspiring. I also want to point out, as people can still see, it's 10:30 your time. So we really appreciate that you come that late at night virtually. And I think with that, we thank you again, everybody.
So folks, this is something that we thought would really encourage discussion amongst not just the speakers, and we've had a great deal of discussion, but it's really to get us going about other ideas, questions, topics. So we've generated some loose questions around what we would like the panelists to think about and answer. And I don't see Joy here, so we can check for Joy whenever she gets here. Yeah, I saw her earlier, so so some questions to get us going, but please feel free to ask each other questions. And again, we'll try to take questions from the virtual audience as well as they come up as well. So if it's okay, I'll get started with the first question. One of the things that we have talked about a lot today is this multimodal data. Some of you are integrating it really well. Some of you are thinking about it. Some of you have given some really good issues for us to be thinking about. But if any of you want to take a stab or give some suggestions on, how should we be thinking about integrating multimodal data? Is it about traditional methods such as timestamps? Is it about collecting all the data and then figuring out scene analysis? How are you all thinking about multimodal data integration in ways that work for you?
I can start with the easiest because I'm snatching it away. But I think Klaus mentioned this. There's some when it comes to synchronization, which I think we wait for Joy briefly. Joy, we started to talk about multimodal data integration, how to do that. So just so you know, the question, if I interpret the question as how to synchronize all of this, which is only part of the question, but I mean there are some solutions. I would be also curious to hear if people in the audience know of solutions beyond LSL, for example, which is something that we've been using, you've been using, and so the lab streaming layer helps to synchronize rather well multiple modalities. Something else I wanted to say. So basically LSL as a question mark, if that does the job sufficiently well. I always remember something I saw on a conference, which I really liked. I found the idea cool. And unfortunately, I think it doesn't work always in all closed room scenarios, which is using GPS. So you have a GPS chip, which has very high time resolution. And if all your devices had that, you had perfect synchronicity, right? And you had the timestamps. But you need to get GPS reception. So I think it would be cool to think a bit more what future technologies would help us to not worry about physical trigger synchronization or anything like that. LSL does a good job without that, but potentially we might need more. And so I'm sometimes thinking maybe 5G will eventually be able to do at least some millisecond precision, which might not be enough for EG, but maybe other modalities. So again, just throwing the ideas out there. This is about the synchronization and not necessarily the integration, but I mean that is, I guess, an important start. If data is not synchronized, very hard to actually do anything afterwards.
Just to provide another thought on that. I think there's something to be said for, rather than integrating multimodal data, to keep them separate and have a focused hypothesis about how data in one particular modality might be related to another. Some of the work that we've been doing, I didn't speak about any of it, is for the same movies to have fMRI and single unit recordings in epilepsy patients. And we don't integrate those. We typically have focused hypotheses that say, you can use the fMRI because you have a whole brain field of view to find some regions of interest, and then you can query single unit recordings or LFPs in that region. But I'm wondering if it always makes sense to just try to put all the modalities together rather than treat each one individually, or take one that has a particular advantage in providing like a initial search and then use that to focus with another modality, perhaps in a particular brain region or a particular time epoch or something like that. So rather you know, pit their strengths against one another in a complementary way. Don't put them all together, but use them sequentially to test, to derive at some mechanistic model.